Hello and welcome to our next episode of Minerva PLM TV. We have again today with us Martin Eigner from Eigner Engineering. Martin, thank you so much for joining me again today.
Hi, Jennifer, and hello, everybody. Do I like to join you? I think it's good. It should be a good meeting, and hopefully it will be interesting. It's an interesting topic, how to transform the engineering digitalization on a concrete PLM system.
Yes, absolutely. And I'm really looking forward to this because we've spent, a lot of time talking about the basics of digitalization of engineering and, typical ingredients like model-based systems engineering or MBSE, as well as systems thinking and new interdisciplinary design methodologies. So being able to get to this next level and focus on that concrete transformation of engineering digitalization on a SysLM like Aris Innovator is really exciting to me. So let's start right off with a quick description for all of our viewers about the vertical and horizontal integration of the engineering process. What does that mean?
Okay, Jennifer, I think you can see in this slide, we have different partial models. So we are always talking about the digital model. The digital model is not a unique set of data. The digital model is split into phases, lifecycle phases. We have a requirement area, we have a system architecture area, we have the design development area, we have the simulation and testing, so the virtual and physical validation and verification. We have the process planning, the production, and at the end we have the operation. So, and we have in each phases we have a partial model, and the vertical integration does mean in every phase we have to integrate the authoring system. For example, the legacy systems for requirements management, for system architecture like Cameo or the enterprise architect, the different CAD systems, the simulation systems, the digital factory systems, and. So I think a typical environment and customer base in automotive and aerospace, we have dozens of different authoring systems, and we have to handle this. So integration, vertical integration does mean to integrate the authoring system, maybe with or without a team data management system direct into the system, PLM, or how I call it, the system lifecycle management backbone.
So
okay, you asked for the horizontal integration.
Yes.
I think the horizontal integration is right on top of the backbone. So we have data in requirement management and system architecture, in design, in simulation, in process planning. And the art of integration is to get a connection between this data. I think we are talking about traceability, digital thread, and all these buzzwords, meaning that we have to integrate the information along the product lifecycle. That is the so-called horizontal integration.
So whenever you think about the next steps, the concrete application that uses all of that data along the product lifecycle and how it's connected, can you describe that for us?
Yes, I will do it based on the definition from Aris. So Aris is using special terms for the applications, and I'm using the Aris terms so it's easier to understand. So we have the functions, the PLM functions, requirements management, system architecture, product engineering for the design, the variant management, simulation management, quality management. We have manufacturing process planning, the so-called MBOM, the manufacturing BOM. We have the manufacturing execution system. We have the digital twin core, and we have the maintenance, repair, and overhaul management. You can see on this slide the green arrows. I think that is what I talked about in the last slide. You can see many green and red colored arrows. The green ones are going forward and the red ones are going backwards. So we have a permanent exchange of data between these different applications. And I think it would be a dream to realize such a information system right now. I think I have never seen any customer who did it. There are some customers in aerospace and automotive, they may have 40 to 50%. So nobody should be upset that he has not realized this nice picture. But we are on the way. So I think the discussion with customers are showing us that they would like to do more and more integration. And I think maybe for the next 2-3 years, we will see the first full integration. I'm quite sure, from requirements to operations, and that is our target.
That's really exciting. And is system modeling an isolated application, or is it also integrated into the engineering process?
Yeah, that's a typical discussion I did with many customers, because 20 years ago, we have this crazy departments simulation, totally isolated, very intelligent people, but no communication with somebody else in the company. It looks like that is a fragmented function. They take over some geometry and they made their simulation, and the result is coming out, but no communication inside the organization. And I'm a little bit afraid, because system architecture, that's a new methodology we are describing, especially for in automotive, in aerospace, and in high tech and medical applications, where we have mechanical, electronic, and software. We have to describe the system architecture based on requirements, function, logical elements, behavior, stakeholder, use cases, and so on. It's a very new technology, and I think we need special people who are doing that, but it's not an isolated application. So we can see in the slides on the left-hand side, we have the input requirements together with stakeholder and use cases. We call this context. And very important, we have a lot of connections in the market with different systems. We can define variance in the early phase. I think very important is all the connection to security, safety, impact analysis, fault tree, FMEA, and physical and virtual simulation. So the real target of the system architecture is to integrate to the left-hand side with requirements, and on the right-hand side with all these types of integration. And then I think we have an integrated solution in our life cycle.
So of course, we've been dealing with requirements for a long time. What does it really mean to have intelligent, integrated requirements engineering? How is that different?
Jennifer, then we have, I think there are many requirement management systems on the market. I know more than 20. And then we have always a question, best in breed or best in integration. So that does mean we have two possibilities. For example, if somebody is using JAMA or DOORS or Polarion or what else, we are able to transfer these requirements based on international standards. There are standards like RegIF, and we can read the requirements and we can store it in the PLM system. There's one possibility. The other possibility is to use the integrated requirement management system inside ours. So we have all ingredients to do requirements management. We can build up hierarchical structures. We can, and it is very intelligent. So you can see it looks like a technical documentation. We have the hierarchy, we have textual representation, graphical representation, and we can connect and we can show, for example, what is connected with the requirements. Are there any parts and bill of materials connected, or is there any system architecture connected, for example, a function or a test plan or whatever? But I think that is the prerequisite to use a good integrated requirement management system.
Okay, that makes a lot of sense to me. And obviously product engineering is the heart of PLM, whether you're looking at engineering BOMs or CAX integrations. How do we handle all of these different types of information?
Yeah, I think you hit it. It's exactly, most of my customers are starting with what we called many years ago as PDM, product data management. That's exactly what we call right now product engineering. I think that is the design, development. So we have drawings. Even now we have drawings. Hopefully they switch over to 3D design, and we have the wonderful so-called engineering bill of material. And we have many information. We have geometrical information. We have structural information. We have different connections, and you can see, and it's a screenshot from ours. On the left hand side, we have all the textual descriptions of the product. We have the bill of materials, the structured bill of material. We have all the connected documents, the non-CAD documents, the CAD documents. So on the harmonium level, we have a lot of functions to connect the part or the assembly with everything else. And in the middle, we have the intelligent viewer. It's a real intelligent view. You can explode, you can cut the geometry. And far on the right-hand side, is something I call the engineering Facebook or engineering Twitter. It's a kind of communication. It looks pretty nice. You can communicate with all the employees or with your customer supplier. You can connect, you can reference drawings and 3D models. You can give any comment. And so I think we have a textual representation, a graphical representation, and we have a communication representation. And that's a typical, that's a typical behavior of a product engineering system. And you have to keep in mind a document or a part or assembly is connected with tons of different solutions here. And that is something a PLM system should show. If you do a change, then the first question is, what are the impacted items? What is impacted by the change? And that's something we can navigate around, and we can get an impact matrix, and the engineer is able to select the really affected items, and that makes a lot of sense and improves the engineering change management process.
Absolutely. So we've talked a little bit about variance, especially earlier, a couple of slides ago, in your description of all of the different elements of connected data. So how do you handle variance in SysLM? What are the basic principles of variant configuration, and how does it all get connected in?
Let's see. I think the theory of handling variance is, I talked about very old. It's 25 years old. In IT industry, it's very old. It's like dogs. They are 7 years, seven years of, no, 1 year of a dog is 7 years in a human life. So I think 25 years in IT is very long, but it's stable. So what we are doing is, the first thing is we have to describe the logic of the variant. So it's typically we have feature families. For example, a feature family is color. Think about the car, the seat, the driver's seat, the material, the color of the seat. And so we have features like color, white, black, beige, or whatever. And we have material, for example, textile or leather or Alcantara. And then you can combine the feature families like color and material with feature. The features is black, white, beige. The material is another feature is the material, the leather or textile or Alcantara. And now you have to combine, you see below the point 3, you can see the rules. You can hit inside the matrix, include or exclude. So you can combine the leather seat should be black and white. Okay, then click in the matrix, and then it's decided. And then what in ours, we call all this, the feature families, the features, and the rules as a variability item. That is a description of the base logic of the variant. And you can see, we can test it on the right-hand side. In the yellow block, we can do the validation. So we can now hit a button, for example, leather, and we can see only C colors are valid. Yeah. And another component is a so-called breakdown structure. The breakdown structure is the structure how the, for example, this armrest is built from. So the breakdown structure shows the armrest. The armrest has some components, and on a lower level, there's a cover. And the cover is defined by the material and the color. So that is a miracle of a variant definition. And at the end, you can see that's another topic you have to do. Now we have defined all the rules. You can see on the label variable component. In the yellow area, you can see a lot of dots that are the represented rules. And on the left-hand side, we have to assign concrete physical parts. For example, if you have a cover, which is leather and white, then this cover has a specific part number. And that's something we have. I think we are not able to do it automatically. That's at the end. It's a manual process to define the instantiated physical parts and components to the rule. And then you can see on the bottom on the right-hand side, you can see the variant tree. You can always show a graphical representation of all the variations. And now you can configure it. It's not, I think the logic in the IT system is relatively easy. The problem of variance is to define the design structure. For example, a car, if you imagine a German car has 10 powered by 28 variant solutions, yeah, then it might be not so easy to describe the variant logic. So my example was very easy because it was only a simple armrest. But I think this armrest can show the base principles of the variant logic.
That makes a lot of sense to me. And what does simulation management really mean, and how is that also managed in SysLM?
Yeah, I think simulation comes more and more because, of course, the target of a digitalization or virtualization is always to reduce the physical test. I think at the end in automotive aerospace, you will have a physical test, but you have to reduce it. And we can show with simulation, we can increase more and more virtual test. And then at the end, we do a physical test. I think the typical behavior of a virtual test or a simulation is we start with the requirements. I think the requirement gives us concrete data, what we should test. For example, if you test the brake system, then you have the conditions with 100 km/h, with a rainy road. We have to stop the car inside 36 meters. That is the requirements with 3 conditions. We build up simulation model. We build up the first system architecture, and then we build up a very easy simulation model based on MATLAB or Simulink or Modelica. I think there's no concrete geometry, but we are able to test on the first level. Maybe we are only able to test 40, 50, 60% of the functionality of the car, but we are able to test it. So we have a simulation model in Modelica, and we test it. And if this shows the right result, I think it will never show the intended results in the first simulation. So what we are doing is many simulation with variation of the data, of the parameter, and at the end the system shows us a solution which is appropriated to go ahead. Then we decided, yes, the base principles of my design and the first level is okay. We go another step. We do the detailed design, typically with CAD. So we have a concrete mechanical model, we have electronic model, maybe we have software code, and now we are able to test with the concrete simulation system like finite elements, noise, vibration, harshness, multi-body systems. So these systems expect real geometry, real electronic layout, or the software code. And I think once again, we are doing test, and more tests, and at the end, we should have the right result. I think the intention of simulation is when you have a physical test, maybe you can do in the car, you can do 40 tests, and then you run out of time and money. In a virtual simulation, we can run the system all the night. We can do 10,000 of tests. So we are really, at the end, we are really secure whether we have a good solution here. So simulation is one of the most important applications, from my point of view, inside the digitalization of engineering. It's a validation and verification.
Absolutely. Those simulations have really come a long way, and it's great to see how the software is now able to keep track of all of that additional critical data as well. So using Eris as our example, and you start to get into the SPDM workspace and dealing more and more with simulations, what are typical connectors that you would see in this type of environment?
Yeah, what Eris is doing, and I think that was a good decision, they bought Comet 2 years ago. Comet was one of the market leaders of simulation system in the United States. And you can see on this slide, the advantage is Comet has a lot of integrations from the geometrical base, so we can direct read different CAD formats, simulation formats. So we have many formats we support by Comet, and then we support nearly all of the simulation tools, and we are supporting the optimization tools. I think we have 3 levels. We have bought with Comet a lot of integration, and that makes real sense, because if you start with the simulation and you have to connect all these integrations, it's a very hard job. It's like the CAD integration. So we bought a system with full integration, and the system is totally transferred in the platform, and the web service-based platform from ours. And it's really a good application.
That's excellent. And kind of taking a little bit of a step back, what is an intelligent FEMA or FMEA?
Oh, FMEA. That's, yeah, but Jennifer, I think 80%, when I come into a company, I guarantee you 80% of, of my companies are using Excel for FMEA. I think FMEA looks a little bit boring because it's a lot of text. Yeah? Well, people, engineers like graphic. The language of an engineer is graphic and not Excel, but they are using Excel. Excel is interesting because Excel has some embedded intelligence. It looks nice, and you can build up calculation formulas and whatever. The problem of Excel is it's not connected to the product model.
Right.
What you can see here in the slide, that is an integrated quality management system. And we talked about design quality documents. Then we talked about a design FMEA. And you can see in the red box, we are using the bill of material. I think the bill of material is directly connected with the bill of material, the engineering bill of material out of the PLM system. And now we are able to connect risk and build on this. It looks like a very intelligent bill of material, but it's partly a bill of material, but on below of each part or component, we can define risk factors. And then the system is able to build up a matrix of all these risk elements, and that you can see on the right-hand side. Now we have to fill in the risk. It's a manual process, but the FMEA structure is tightly connected to the bill of material. And everything, the documents, everything is connected. We would like to see, in the definition of the FMEA, we would like to see a document. You hit the button and you can see the document there. It's a full integrated quality management system. So the engineering change management is connected. Typically, if you have a quality problem, you will get a problem report. And typically, you can see it here. You have an engineering change order. So the new FMEA, the risk analysis, is part of the engineering change management process inside this screenshot. And that's interesting. Once again, it's not only connected to the bill of material and all the documents from the design, it's connected to the processes, so the engineering change management. So quality management could be integrated in the product model and in the process model. And that shows, once again, the advantage of an integrated solution.
Absolutely. Having all of that visibility in one place and the connected data and being able to see how change management impacts the quality findings and whatnot is really the next level. So talking about reducing, disparities and redundancy and all of those kinds of topics, how do you, or what is the solution rather, to get rid of redundancy between EBOM and manufacturing process planning and MBOM translation and all of these different base principles?
Yeah, that's another. I think we have many topics. If you walk through a company, there are some topics that are really political. I think a numbering system is one of these topics. If you discuss numbering system, it's really crazy. Another topic is if you talk about EBOM, MBOM. That I think between EBOM and MBOM, there is a chasm or a big gap, because the EBOM is belonging to the R&D department, and the MBOM is belonging to the manufacturing department. And I think there is a barrier between them. And we have to see it's not only the barrier in our brain, it's a barrier from IT system. On the one hand side, typically we have a PLM system. On the other side, we have a MRP ERP system. There are different organizational units. And okay, so coming back to the discussion, today we have a general trend. It's not only based on PLM, it's based on manufacturing execution system, because the MRP system are typically 30 years old. They have not all the functionality we need for a modern lifecycle management, for configuration management, change management. And there's a trend to take over or to shift function from MRP, ERP to PLM and to manufacturing execution system. And one of this discussion is to do the manufacturing process plan and the MBOM from the PLM side. And we did some research and we discussed with companies. Typically in our brain, it's fixed. We have an EBOM, then we have an MBOM, we transferred. The best would be EBOM and MBOM is the same. But when you discuss with an engineering employee and the manufacturing employee, that it's impossible, we can't do that. And even in easy construction, like an electrical engine, we have a difference between EBOM and MBOM. That is a little bit a cultural problem of our history. We are not willing to change ourselves. But anyway, we have the EBOM and the MBOM. And then when we have the MBOM is a starting point for the manufacturing process plan. Mm-hmm. So we did, together with the customer, we did something totally new. We said, the EBOM, I think the number of parts and components at the end, or especially components, single parts from EBOM and MBOM are the same. And so we did something very easy. We used the flattened EBOM, and with drag and drop, we created the structure of the manufacturing process planning. The manufacturing process plan is connected to the MRP system. We can access to all the resources like machines, skills, tools, and so on, and we can build up a manufacturing process plan. And then we can, at the next step, we derivate the MBOM out of the manufacturing process plan. It may be a non-persistent BOM, you can do it persistence or not, but it is a derivate out of the MVP. My fundamental problem since 30 and more years, and even when I worked for Bosch, we have a CAD structure, we have an EBOM structure, we have an MPP structure, and we have an MBOM structure. And then we have different plants when we have a parallel production in Shanghai, in Italy, and in North America. We have the structure copied many times. So it may be in a company you have 7 very similar product structures, and it makes me nervous because you have to maintain these product structures. So what we try is we try to combine EBOM, MBOM, and MPP, and we are successful. And we can do a so-called reconciliation. When we do a change in the EBOM, we can see the change in the MBOM. I think that's another important fact. Typically, we have a change management in engineering for the EBOM and a change management in the MBOM on the MRP side. Now we can do everything on one place in the PLM system. It's fully integrated, and we get rid of one structured MBOM.
Yes, and nothing gets missed because it's all connected. It's a beautiful
thing. It's always, whatever we discuss, it's based on integration. Mm-hmm. Yeah. If you do not integrate, I think it's a hard job. If you have different systems, and that doesn't mean that you have a monolithic big system. So we are working in the cloud. We are working based on web service, microservice. We are containering our software. So it's not the monolith. It's a widely connected system. Mm-hmm. But this is one central repository where all the informations, the metadata of the informations are stored. Yeah.
Mm-hmm. And all of this connection really does help enable things like the digital thread and the digital twin. So how do you create a digital twin out of the variant configuration and the serialization of this digital twin?
Yeah, I think that's the end. Now we are facing directly the MRP environment, but I show it on the PLM side. As you remember from the generation from the armrests, we will get maybe around 400 different types of armrests based on material and color combination, and integrated armrests, non-integrated armrests. So we have many different features. And then at the end, we will get bill of materials, concrete instantiated bill of materials. A variant configurator, when we have method from the mathematical point, and based on the rules, we may have 600 possibilities of variants, then we may get 400, 500 different bill of materials for each variant. And this variant must be transferred to the order management. So in ours, what we have to do, we have to release the bill of material, and then we have to build up a physical part. Physical part means now we can produce it. It's not I don't like the name physical part because it's not physical, it's still virtual. After production, it will be physical. But anyway, I'm not responsible for the terms of the PLM system. So we transfer a virtual engineering part coming out of the variant configurator. We build a physical part, and now we can do a lot of things. We can define, typically in automotive industry, we are working with serial numbers or charges. We decided we will do 220 armrest, and then we block 220 serial numbers. So each instance of this white armrest will get a serial number connected with a part number. So that is very important to keep track, to trace a concrete armrest in a specific car. Maybe in your car, if something is broken, we can trace back based on the serial number to the part number, to the configuration, and we can explore what was the bug here. So now we have the physical part. We have defined, yes, we keep track of the physical part based on serial number, and now we can assign the manufacturing order. And this is typical in the environment. That's the German customer of automotive supply industry. The manufacturing order is transferred to the MRP system.
Mm-hmm. And how do you create this concrete manufacturing order?
Yeah, the manufacturing order is an item in the PLM system. That's new because manufacturing order is typically assigned to the MRP environment. You can see here we have the manufacturing order. We have defined the serial number. We can see the MBOM. We can see the development BOM. In this case, it's the variant configuration because we have no concrete EBOM. We have the variant configurator, and then we can see the actual serialized order BOM. Yeah, that is in one display where you can see based on the writers of the harmonium definition, we can see different instantiated structures, and I think the blue box is sent to MRP. That is the order-oriented MBOM.
Okay, that makes a lot of sense to me. So from there, you kind of move on to the next phase, which would be MRO, maintenance, repair, and overhaul. Yeah. What are the base principles behind MRO?
The MRO, it's another new application combined with PLM. And once again, ours has bought one of the market leader in MRO, Empresa, and the system is just transferred to the ours web platform. The typical function of the MRO system is we have to first we have to build up a digital twin. I think now we are in this discussion of the digital twin, but you can see what you have seen in the last slide. We built up a digital twin core when we assign a serial number to an instantiated produced part. For example, the white leather armrest with the part number 4711 and with the serial number 2022. Then it's a concrete, singular, unique twin base. I think it's a one-to-one assign between the physical component armrest to the virtual component. I think the digital twin is the prerequisite to build up an MRO system. Now we have the first thing, an error is coming up. We have to detect the error. Then we have to build a program report. We have to write, maybe we have to build up some reports. Maybe we have to have some logistical problems to get spare parts or whatever. Then we have to replace the faulty part, and then we may have to initiate a corrective action plan because a bug in a part or a component may show that the design may be wrong. So we have to change the design for the next generation of parts. There are the 4 elements of an MRO we have to realize. But the basis for all is a digital twin and the traceability based on the serial number.
Absolutely. And I think a lot of that, having the foundation of the digital twin as a prerequisite to MRO is really obvious in industries where it's difficult to get out to service whatever the manufactured product is. I mean, like windmills or, something very large like that, that's sort of stationary is a great example. But, it has a trickle down effect to all industries. Really, it makes it much easier if all of your data is connected and you have that digital representation of the physical.
Yeah, you're right.
So,
I think that the digital twin is a real. It's not a buzzword anymore.
No.
I think most of the new initiatives in the PLM area or environment are MRO and digital twin topics.
Absolutely. So how does SysLM handle problem reports, service bulletins, and the documentation of the instantiated digital twin?
Yeah, I think in the next slide you can see on the one hand side you can see the I think in the green box you can see the instantiated digital twin. I think that is the actual bill of material, and you can see there's in the yellow box there is a problem report. The problem report is sent from the field. Something happened. There was an overheating of a sensor, and based on the problem report, there was built a service bulletin. The service bulletin is a start inside the company how to handle the problem, how to solve the problem. I think that is there are some communication in the blue box. We have once again our engineering Twitter, so we can communicate between sales, spare part department, and whatever. I think that is a document. The digital twin is documented with the serial number. We just jump into the digital representation of the one and only digital twin related to the serial number of the robot arm. And now we execute. We will build a work order, and we execute. You can see here we have fixed the problem. So we have substituted the sensor. We have a new serial number. The part number is the same, and we can see in the red square we can see graphically what's happened. So we have the robot arm. We have all the potential customers. We have work orders, what is done for the other customers, and we can see what's happened. I think I think it's not, the problem is not the only robot arm. Maybe we have 500 robot arms in the field. We have to keep track. We got an error. Now we have to analyze in a quality management action. Is this a bug who is able to occur in the other robot arms? So we have to make decisions to predict errors in the future for all the other customers. I think that's a complicated connection between maintenance, repair, and overhaul, quality management. I think many information should give a feedback to engineering what happens in the field. I think that is an educational point for engineering when they can see graphically and connected what's happened with their parts and components and products. I think that should be very good now. And we are faster to handle the customer.
Yes. So as our last point here, how is the documentation of MRO really the actualization of an as-maintained MBOM?
Yes, I think that's a hard job. You can see here in the green box, we have substituted the sensor. I think there's a red cross, it's the old sensor, and it's not a new sensor. And we have to keep track even from the history. So we can see when, where, why we have substituted this sensor. And I think it's a bill of material. I think at the end, the as-built bill of material is the starting point. We call it foundation or core of the digital twin. In reality, we do not need every component of the bill of material. For example, in the car, we don't need the windshield wipers because the customer, the driver, is able to exchange the windshield wipers, so we are not able to control it, or even the tires, because everything what the driver or the owner is able to substitute or to maintain by himself. We don't need to, in a bill of material, in a trace digital twin bill of material. So we can get rid of many things we don't need. But at the end, the basis always is a as-built, a concrete as-built bill of material. But maybe after 2 years, this concrete bill of material of a digital twin looks totally different based on exchange components.
Mm-hmm. Yes, absolutely. You know, Martin, this has been such a lovely journey. I've really enjoyed all of the sessions with you, going through how we arrived on PDM and that need at all, and the total evolution of product lifecycle management, arriving today with the concrete instantiated example of systems lifecycle management, and really being able to have that fully connected vision that we've been striving for so long. Thank you so much.
Okay, let's go forward in the engineering digitalization. Okay, Jennifer, stay healthy. Good luck.
Thank
And see
you.
you.
Same to
Bye-bye.
you. Bye-bye. And to
Bye-bye.
all of our viewers, thank you for joining us. If you like this content, remember to hit the like and subscribe buttons to be alerted to future episodes. If you have a question that you'd like to see answered, drop your comments below or send me an email at jmo@minerva-plm.com. Thanks, everyone, and have a wonderful day.